This is our poster project on Qdarts, a neural architecture search framework that includes mixed precision quantization search. In this poster presentation, I will cover why we needed to create this architecture, how Qdarts works, our experimental results, as well as some conclusions and future work we can draw from this project. For edge computing especially, it is necessary to quantize neural networks so that it can run faster, use less power, and occupy less disk space. However, most neural architecture search methods do not consider quantization during the search, and when they do, they have drawbacks, which we will talk about shortly. We developed Qdarts to efficiently find mixed precision quantization configurations during the architecture search phase. Let me quickly go over the state-of-the-art methods and explain why they are lacking in several regards. Normal neural architecture search methods like darts do not consider quantization, so any quantization must be applied later with no guarantees about how the quantization will affect the performance on the network. True, there are some quantization-aware neural architecture search methods. However, these methods involve costly multi-stage optimizations where search is performed for the architecture and then separately for the quantization policy. On the other hand, there are some methods like EDMIPS, which just search for mixed precision configurations for a static network structure without neural architecture search. Of all these techniques, Qdarts is by far the most flexible solution. Qdarts incorporates the efficient neural architecture search of darts, but it also uses differential quantization policy search during the search and the end-to-end joint optimization. Now I talk about our proposed solution, Qdarts. First off, as shown in this cell, the blue, we apply the same weight sharing technique as darts. We also use the same mixed quantization layers as EDMIPS, which I show in the orange box. In this manner, the entire mixed precision network is fully differentiable. It is not shown here, but we also apply the complexity penalty of EDMIPS so that our discovered network favors lower complexity structures and bit precisions. To evaluate how effective Qdarts is, it is necessary to benchmark it against other alternate approaches. The most obvious benchmark is applying post-training quantization to the highest performing architecture found by darts, shown here. The second is applying a quantized aware training to the same network. The next benchmark would be to apply mixed precision quantization search, or EDMIPS, to the subnetwork found by darts. We call this baseline Qdarts subnetwork. Finally, we test Qdarts supernetwork, which combines darts and EDMIPS search into one joint search. Now to move on to our results section. The bar chart on the left shows the performance of our darts subnetwork with post-training quantization for various fixed bit precisions. The y-axis is accuracy. Interestingly, we see that 4-bit post-training quantization performs quite badly. The chart in the middle, on the other hand, shows our method, Qdarts, benchmarked against other high-performing baselines. On the x-axis, we have the bit operations per network, and on the y-axis, we have the network error. If you look at the blue line, you can see our 4-bit and 2-bit quantized aware training results. The 4-bit quantized aware training has much lower error, but uses double the resources of the 2-bit. The next bullet we see slightly under the line is Qdarts applied on the subnetwork. As you can see, applying mixed precision architecture search to the Dart subnetwork increases the computational efficiency while maintaining the same error as the 4-bit. Next, we move on to the approach with the lowest error on the bottom, which is our Qdarts supernetwork approach. As you can see, the computational complexity is midway between 2-bit and 4-bit, but has a vastly lower error. This indicates that our approach was able to find a lower complexity model that performed much better within a fixed computational budget than our baselines. Now the right graphic. We can see the discovered cell structures found by our approach. They are a bit hard to see, but we found that they are far less computationally complex than the cell structures found by the original Dart search. Although we do not show it here, we verified that the subnetwork found by Qdarts contain a mixture of both 2- and 4-bit operations. To conclude our presentation, we have found evidence that applying Qdarts on the supernetwork works well compared to other methods. Specifically, we have found that applying Qdarts performs much better than applying quantization after darts or performing a mixed precision search after darts. However, We need to run more experiments so we can detangle the individual contribution of mixed precision search versus the added complexity constraint. That concludes the poster demo.